So in this talk, I would basically like to talk a little bit about how visualization can help to understand player activity, understand playtesting data. And I would just like to do that with a couple of examples of approaches we came up with recently. Just a few words about myself. I'm currently working in academia. I'm an assistant professor at Eindhoven University of Technology, and I'm also holding positions in Ontario Tech and in Vienna at the University of Applied Arts in Vienna. And here you can see a couple of things I have worked on in the past. And one of my main interests with respect to games user research and games analytics is on visualization of in-game data, of player-related data. And I'm basically a big proponent of visualization because it can offer many benefits for analyzing data. And first and foremost, good use of the cognitive and facilities of humans, quickly perceive and comprehend information in a visual way. And because of that, it's also possible to easily perceive large amounts of data and also to see patterns within that data. And that can be very valuable. But of course, the visualizations need to be designed in a way which allows for that. And if we're talking about interactive visualization, it also allows us to view data on different levels of detail, which can also be very valuable. And apart from that, it's also very helpful to communicate findings, which can be especially of value when working in a team where people have different backgrounds and expertise. And all these benefits make visualization also a good tool for working with player-related behavioral data. Data collection is basically easy, but the challenge is to make good use of the data. And that can be quite challenging because often it's very large data sets, and sometimes playtesting also uses different data sources like telemetry data, physiological measurements, or interviews to gather feedback. And by integrating those different data sources, we can also better make use of their potential. And as part of that, visualization can be very useful and important tool to efficiently analyze and understand the data we have collected. And I mean, of course, there are many different application areas where visualizations can be useful. Today, I would like to focus on two aspects. First, I would like to talk a little bit about how visualization can help to understand movement data, which I think is quite important because almost any game has a certain kind of spatial component to it. And secondly, I would like to show a couple of examples of how visualizations can help to triangulate different data sources to better contextualize the data. And throughout the talk, I also put a little bit of emphasis on different ways to aggregate the data, which can be helpful for achieving a non-cluttered view when we are dealing with large amounts of data. So starting with movement analysis, I would like to, so instead of showing how to visualize raw trajectories, I would like to show an alternative based on semantic trajectories. And these can be very helpful for achieving a high-level summary of player movement. And the basic observation of semantic trajectories is that in many cases, the exact coordinates are not really necessary to comprehend movement. so let us assume I would like to tell you about a nice day I spent in Barcelona, and that could then happen like that. So I basically stood up quite early and left the hotel, made my way to the famous park designed by Gaudi. And after that, I went to visit the cathedral in the center of Barcelona. And then I would take a nice stroll towards the old center, got a little bit lost around here, did a little bit of shopping, and then made my way to the beach to spend a lazy afternoon fare before heading back to my room. And the interesting observation here is that when I record my day, I rather focused on the sites and locations that I have visited rather on the actual routes that I have taken. And this is basically the concept of a semantic trajectory. It abstracts from the actual routes taken and rather focuses on the order of locations which have been visited. And we thought that might also be a very nice concept to apply to games, because also here, it's not always so much of interest about the actual routes a player has taken, if a player was moving a little bit more to the left or a little bit more to the right, but rather about certain areas of interest which have been visited while playing. And so we developed a tool based on that concept, and it's basically a 3-step procedure which we follow here. And in the first step, we basically track the players while they are moving around in the virtual environment. And then we allow the user or the analyst to define certain areas of interest. This could be, for example, an area where an important item is located, which is necessary to proceed further in the game, or also areas which correspond to junctions in the level environment, for instance. And based on those areas of interest and the tracked movement data, we can derive the semantic trajectory, which I just indicated here roughly using the red line. So that's basically now the sequence of areas of interest. And once we have those semantic trajectories, we can analyze that. And for that, we currently offer 3 different views. And the first and main view is a transition diagram, which shows the amount of movement happening between the defined areas, which are shown here using the brown rectangles. And the width of the arrows basically reflect the number of transitions and happening between those areas. And having those semantic trajectory also gives us another advantage, because we can now also establish the similarity between paths. And in our case, we do that by using hierarchical clustering performed on the longest common subsequence of the paths. And the result is then shown using a dendrogram. And that's basically an interactive chart where the user can select group of paths or outliers, for instance. And finally, the 3D view allows to view the detailed tracked trajectories. So this is, for example, an interesting case where a player found an unintended path by climbing over a couple of rocks into a room, and then got stuck in the room and could not escape anymore. So yeah, that's basically the 3 different views offered by that visualization. And those are all linked. So if somebody selects something in the dendrogram, then the other 2 are filtered regarding that selection. And so semantic trajectories are also quite helpful for aggregation. And they can also serve as a useful building block for other visualizations. And here's another example where we made use of semantic trajectories, and which is a visualization which was intended for team-based games, and where we took inspiration from so-called battle maps, which you can find, for example, in many history books, and which provide a visual representation of how a battle has unfolded. And the algorithm we came up with basically takes as input movement data and data about attacks between those units and creates a battle map out of that. So I can't go too much into detail, but briefly summarize the algorithm first detects areas of intense fighting by clustering the locations basically. And then we calculate also long distance attacks between those regions. And in the next step, we basically aggregate the unit movements. And this is done by first subdividing the environment into small regions. And those regions are basically used to simplify the raw trajectories. And in that way, we can transform them into semantic trajectories. So each unit is then represented by the sequence of regions which have been visited. And again, because of that, we can then group those trajectories based on the similarity. And for each group, we can then define a representative trajectory, which basically is the average of movement in that group. And by using the average, what is the representative trajectory, the identified regions and the long distance attacks, we can then assemble the final visualization. So here's an example using actual gameplay data. This is data from a World of Tanks. On the left, you can see the input data, and on the right, you can see the output created by the algorithm. So this was, when we evaluated it, it was pretty well received, but it had one major drawback, and that was the overlapping of some of the movement errors, like here, which made it difficult to see where the splitting happened or how many units actually moved in a certain direction. And so we refined that a little bit later by merging the individual errors to better convey the splitting and also the merging of troops, and also to better convey the total troop strength. Here on the left, it's basically the solution achieved with the original algorithm, and on the right, you can see the improved version. So with that, I would like to maybe change to the second part and show a couple of examples on how visualization can be helpful to triangulate mixed data sources. And for that purpose, I will make a very rough classification of playtesting data. I mean, of course, there are many different ways to do that, but I think that suits the purpose of the presentation. First, I will consider discrete events. So basically events which happen at a certain point in time, like picking up an item or an observation which was made while coding a playtesting video, for instance. And secondly, and in contrast, we have continuous data, so basically data which changes frequently, which could be, for example, the health of the player, or it could also be physiological data, for example, measured through a sensor. And third, again, movement data, which of course can be considered continuous data source as well, but which I treat here separately because I think it's so important in so many games and deserves to be treated separately when visualizing the data. So as a first example, I would like to show one using data based on Super Mario Brothers. And in that one, we tried to triangulate movement data, physiological data, basically arousal measured through galvanic skin response, and discrete events, which are basically observations coded during observing playtesting videos. And what you can see here on that slide is basically the representation of the individual data, where the lines of course, show the movement, and the color coding reflects the arousal values. In that case, yellow would indicate low arousal and red would indicate high arousal. And the small icons you can see scattered across the image are basically the discrete events are coded from the playtesting videos. And different icons correspond to different events. And I mean, showing it individually already gives some impression of what's happening, but it also has a couple of drawbacks. And first of all, first the issue of occlusion. So for example, if we are looking at the icons, and if there are many icons in near proximity, then those are overlapping each other, and it's quite difficult or even impossible to see which icons these actually are. Secondly, visualization of individual data is quite prone to visual clutter. So for example, in that area, there was a lot of jumping going on, which resulted in a visual mess, basically, which makes it quite impossible to understand what's going on here. And one might think that's just an issue if you're having a large number of players, but this is actually based on just 6 players, and the problem is quickly getting worse and worse. And lastly, and that's more specific to movement now, it also provides a misleading impression about the amount of movement. So for example, if a lot of players are taking the same path, then each path is plotted on top of each other, which makes it appear as just one single player was moving. And of course, it's also about occlusions again, because now we cannot see the color coding of the other lines anymore. And to counteract some of those drawbacks, we basically perform a couple of aggregation steps to simplify the representation and to better show general patterns in the data. And in that case, we are doing that by first clustering the discrete events. So we basically group events of the same type within a certain vicinity together, and then we replace those using a single icon. And the size of the icon now reflects the number of events. So the basic idea is to reduce the number of individual elements so that the visualization is getting more and more simple. Secondly, we take care of the actual movement, and we do that by first subdividing the level environment into small non-overlapping regions, similar to what I have shown earlier in case of the battle map visualization. And then we replace the individual lines with lines showing the amount of movement happening between the individual or between adjacent cells, basically. And now we can already see a better distribution of where the main movement has taken place, for instance. And lastly, it's about the continuous data. And for that, we use the cells which we created for the territory tessellation, and we color code those cells. So for instance, we could visualize the average arousal value in a certain area. But of course, it could also be the maximum or minimum or something else. And that way, the tracked continuous variable is also shown in relation to the actual movement. And here's a short video of how that looks like if we are taking everything together. I hope that's working. So basically we do the clustering. We perform the trajectory aggregation. And lastly, we color code those cells. And that's how the final result looks. So this was basically a 2D solution, which of course also works if one can project the 3D data onto a 2D plane. But of course, that's not always possible. And here's another visualization we came up with, which was done in 3D, and where we tried to triangulate movement, gaze, and emotions. So again, the user can observe the individual paths of the different players. And again, it's possible to aggregate the paths to achieve a less cluttered view of the data. For example, the back and forth, which is happening in that area, is now much more visible than in the individual representation. And in that example, it was basically a door which had, where the player had to enter a key, a code, and the code was located on a code sheet in another room, which could not be picked up by the player. So if the code was forgotten, the players had to run back and forth to finally be able to open the door. And yeah, so secondly, we also track the gaze. So that's done through an eye tracker. And then we use the data from the eye tracker, performed raycasting, and calculated the observed object. And the color-coded silhouettes, which you can see here, is basically indicating how long a certain object has been observed. And lastly, we recorded the players using their webcam and then extracted the experienced emotions from the video stream. And because it's quite likely that players have a neutral expression over long periods of time, we rather focused on changes in the emotional state of the player. So we basically transformed the continuous variable into a discrete one for visualization. And the particle systems you can see here indicate the different types of emotions. Yeah. So again, here's a summary of how that would look like for one player. So for example, and I think that already gives a little bit better impression of the overall activity or experience than just movement alone, because now it could be possible to see if a player was actually frustrated while running back and forth, or if the player was actually having a good time. Here again is a short video to just show how that looks in action. So if a particle system has multiple colors, then that's basically indicating that there were different types of emotions experienced in that area.
So Günter, you have just a couple minutes left. Do you want to wrap up and go to questions?
That's fine. Yeah, I'm basically at the end now. Okay. So we can move on to questions. I'm just, yeah, just have a couple of guidelines, but we can discuss that afterwards as well. Yeah, thanks for joining, and then just opening the question answer screen to see.
So you have a question from Daniela that says, how do you collect the data that is being plotted in this spatial visualizations coordinates? And do you track it from all players?
Yeah, so basically, I'm not sure to which visualization that refers to, but yeah, it was basically tracked coordinates in fixed time intervals. And for the Super Mario example, we tracked it for each player. And in case of the battle map, for example, this was extracted from replay files, for instance. Yeah. So I see another one. How are you making these visualizations? So a couple of those were made with OpenGL, for instance, and C#. and others were directly integrated into game engines. One I have shown was done in Unity, and another one was integrated within the Unreal Engine. What does the color coding of the cells represent? In that specific example, I have shown it was basically arousal of the players. But of course, it could be any variable of interest you could represent that way. One advantage doing it that way is that you can have in the area, for example, not just the amount of an event, but also a certain statistical indication, like, for example, average or something like that as well. I think the next question I answered already before. How do you create those visualizations? How much work do you anticipate needed to either make this type of visualization code generic, or if that's not possible, for a given development team to tailor the software to their own game? So basically, we try to keep everything quite generic. So it's not so much about the game, but rather on how the data is tracked, yeah, and which type of data it is. So basically, the Super Mario example, you can easily exchange the data because it's basically relying on movement and continuous data, which was tracked. So there's another one, great visualizations. Do you feel it's harder to use those techniques for 2D games than 3D titles? So basically, what I feel is that visualizing in 2D, of course, has certain advantages because navigation in the visualization is easier. Because in 3D, you usually have to navigate through the visualization, which might impede the overview which you get on the data. Do I have time for one more, or are we running out of time?
One more, and then we'll give Ashley the floor. Ashley can go long if she needs to.
Okay. Can you explain a little more on how you got the emotions data? So basically, in a nutshell, we tracked the players using the webcam and used the Affectiver SDK to extract emotions. So that SDK basically extracts the 6 main emotions of humans. Yeah, and that was basically it. Okay, thanks for all the questions. Yeah. Yeah, you can also reach me through email or on Twitter as well.
Awesome. Thank you, Günter.